Yesterday in class, we were working on a problem that is classified as an optimization problem in calculus. Optimization problems try to find the maximum or minimum of something like volume, area, distance, cost, etc. What we were trying to do yesterday is we were trying to maximize the volume of a box based on cutting out squares out of the side or out of the corners of the piece of paper that we had. So what you have to do with optimization problems is you have to try to come up with a formula for what it is that you're trying to maximize or minimize, and then use a little bit of calculus to figure out what the values are going to be to get that maximum or minimum. So I've typed up some steps that you should copy into your notebook on how to solve these maximum or minimum problems. What we did yesterday in class is we came up with an equation, we took the derivative, and when we took the derivative we set it equal to 0, and then we solved that for x. So here, I'm not going to go through this specific example. I just want to have you put in your notes what the steps are to do a maximum or do an optimization problem. So let's say we have come up with a problem that we want to try to maximize or minimize. Well, we have to read the question very carefully. Hopefully you can read this all right. And so in the problem, what you need to do is find out what you're trying to maximize or minimize, and it'll tell you in the problem. Once it tells you what to maximize or minimize, you need to draw a diagram, identify given information, and identify the required quantities, or usually we call those x. Hopefully you can read this. After you get done drawing the diagram and figuring out what it is that you're trying to maximize or minimize, then you need to go into the algebra part of it and write an equation. Like if you're trying to maximize volume, use V for volume, or M for material, A for area, whatever it is, just use a meaningful variable. And use descriptive variables, because if you are sloppy in optimization problem, you kind of lose track of what's going on as you go through the problems. So you always have to keep in mind, what is it that I'm trying to maximize or minimize? The next step is trying to get the equation in terms of two variables, like y equals some function of x. Like in our volume problem yesterday, we came up with the v function. The v was equal to x times, I think it was 12 minus x quantity squared. So you can take the derivative. And then the next thing you have to do, oftentimes create a second equation from additional information. That's not always the case, but depending on the problem, you're going to have to do that. Isolate one of the two variables in the equation. And in the original equation that you're trying to maximize or minimize, replace the variable that you isolated in step 3b. Sometimes these middle steps don't have to be done. Like in the volume problem we did yesterday, we only had one equation in terms of two variables, so it wasn't all that complicated. We didn't have to go through these middle steps in here. But as we go through this chapter, this portion of chapter 3, we'll get some problems that are a little bit trickier, so we will have to do the intermediate steps in step 3. Let me put this back a little bit. All right, then once we get everything all written in terms of y equals f of x, you have to take the derivative, set the derivative of equal to 0, and solve for the value of, usually solve for x. And that's what it means to optimize something, is setting the derivative equal to 0, because you're either maximizing or minimizing something at this point. Boy, is this blurry. There. So if you need to pause this because you couldn't read it very well, go ahead. Get these in your notes. And then after you set the derivative equal to 0, you have to find the critical numbers. And if you have a closed domain, like we had yesterday, the closed domain, we had the x was the size of the little boxes squares that we cut out of the corner. So x couldn't be negative and it couldn't be greater than 6, I think it was. So you have to compare the function's value of the critical values to that of the endpoints, because sometimes your endpoints will be what the variable's values are for this maximum or minimum problem. And if the domain is open, which means it could the endpoints are not included, all you have to do is do a second derivative test. And that's probably the quickest way to see if it's a maximum or minimum for the concavity. And then the last step of all is once you figure out that variable and you figured out that it is a maximum or minimum based on either the second derivative test or the first derivative test, you just plug that value of the variable back into the first two equations to find the dimensions, or just answer the question that's being asked. So that's the 6-step process to an optimization problem. And I'm going to go through a specific example, and then we'll go through lots of other examples in class to practice this stuff. So let's say, for example, we want to find the minimum distance from the graph of y is equal to the square root, how about 3 times the square root of x, and the point 5, 0. And that's just it. That's your question right there, the minimum distance from that graph to the point. So since that's the only thing that's given to us, what we want to do is graph this equation. So y equals 3 square root of x kind of looks like that. Hopefully you know what that looks like without a graphing calculator. And here's the point called 5, 0. Now distance, when you're finding a minimum distance, you need the distance formula. The distance formula is the square root of x1 minus x2 squared plus y1 minus y2 squared. But in any distance problems, if you're ever trying to minimize the distance, you're trying to minimize the distance between here and there, and you don't know exactly where this is going to fall on this curved space, so we're just trying to minimize this distance right here. So this point right here, this is just called xy, but y is equal to 3 square root of x, so what we can really call this is not xy, but x comma 3 square root of x, because that's what y is equal to. And then we have our whole problem in terms of only x, not x and y. So if we're trying to minimize the distance, if we ever have to use the distance formula, what we can do to eliminate this square root issue, we can minimize, and it's going to make our life a lot easier, the square of the distance. Because if the square of the distance is minimized, so is the distance. So it just prevents taking a derivative of a radical, which sometimes gets messy. So the distance squared is just x1 minus x2 squared plus y1 minus y2 squared. And if we minimize this, then we've minimized the distance, and this is going to be a much easier derivative to take. So what we have here is we have an x1, y1 in this point, and we have an x2, y2 in this point. So x2 will be equal to 5, y2 will be equal to 0, and this is the distance we're trying to find. So our x1 is equal to the variable x, and our y1 is equal to 3 square root of x, or y1. So we're going to plug x1, y1, x2, y2 in this distance formula, take the derivative, and set it equal to 0, and make sure that we've got a minimum distance. So x1 is just x, x2 is 5, y1 is 3 square root of x, and y2 is 0. So we're going to minimize this. So what we can do, it doesn't really matter. I usually just FOIL this out, x squared minus 10x plus 25, and minus 0, it just doesn't, the 0 doesn't matter, so you're going to square 3 square root of x. 3 squared is 9, and square root of x squared is x. And when you combine like terms, you get x squared minus x plus 25. So there's the distance squared, but we're going to minimize the derivative of this. So we'll just call this d for what we're trying to minimize. So if we're going to try to minimize d, we're going to have to take the derivative, and the derivative is 2x minus 1. We're going to set it equal to 0, and we get x equals 1/2, and that's our critical value. Our domain of this is x has got to be greater than or equal to 0. So we also have to check the endpoint. Now this x does not have a maximum, so we don't have anything else to check on that. So we're going to check the x equals 1/2. We're going to check the distance between x equals 1/2 on this point up here and 5, 0. Okay, now first we have to make sure that's a minimum. So this is the d prime sign table. D prime is 2x minus 1. Our critical value is 1/2. So if we choose a number less than 1/2, like 1/4, this will be a negative value. And if we check something bigger than 1/2, this will be a positive value. So what we have is a graph that comes down and goes up. So we have a minimum point. I did a first derivative test. I guess that's just, it would probably be easier to do a second derivative test because the second derivative is always positive, so you would get a concave up graph. But anyways, 1/2 is the minimum, a minimum point. So now, since x equals 1/2, all we have to do is plug x equals 1/2 up into our y, and actually we're finding the minimum distance from those 2 points. So when x is equal to 1/2, y is equal to 3 times the square root of 1/2. And the distance, what we're trying to find is the minimum distance. The distance is equal to the square root of x1 minus x2. Remember, we're still finding the distance between 5, 0 and that point. That point right there is 1/2, 3 square root of 1/2. So our distance formula is x minus 5 squared. X is 1/2 minus 5 squared plus. And then the other point is 3 square root of 1/2 minus 0 squared. And this will give us a minimum distance. And now it's time to take out our calculator because this is going to be a crazy fraction here. Or crazy decimal, I mean. So the minimum distance is the square root of 1/2 minus 5 squared plus 3 square root of 1/2 squared. And 4.975, I'll round it to 3 decimal places. The minimum distance is 4.975. Hopefully you saw that on my calculator. I don't know if it was underneath or not. So we got 4.975. Now our other critical value was x equals 0 because that's the endpoint of a domain. And if we wanted to find the distance between this point 0, 0, this distance from here to here is 5. This distance from here to here is 4.975. So this is actually the minimum distance between the 0.50 and the 0.3 square root of x. So I think we've got our answer. If we tried to find the distance between 50 and any other point on this graph, then we would get some larger distance than that. So that's our answer. And that's it for today. We'll get a lot more practice on optimization problems all week long. Hope you had a great weekend, and I'll see you Monday.